Well, hello there. Today we're going to talk about continuity, or where a function is continuous. Now, in plain English, the word continuous means something that is unbroken or connected, and we have a much more mathematical definition for the idea of a function that is continuous. So a function f is continuous at a number a if the limit as x approaches a of f of x is equal to f of a, meaning the limit of the function at that point is equal to the function value at that point. And then otherwise we say f is discontinuous at a. Now I want to note that this actually places three requirements on the function. First of all, the limit must exist as x approaches a. Secondly, the function must be defined at a. That value a must be in the domain. And third, the limit and the function value have to be equal. If any of those things fail, then the function is discontinuous at that value a. Let's take a look at a graph to see some ways that functions can be discontinuous. So here we have a graph of a function. We can call that function f of x. And there are different places where this function is discontinuous. Let's take a quick look here. First of all, we have a discontinuity here. And the reason we have a discontinuity there is because the function is not defined for that value. We can call that value a, just so that we have a name for it. And there's a name for that type of discontinuity. We call that a removable discontinuity. A removable discontinuity occurs when the limit as x approaches a of f of x exists, but it is not equal to f of a. So in this particular graph, this occurs at x equals a, and then also at this point here, I'm going to call this c for reasons that will be clear in a moment. Just want to make everything alphabetical. But this also occurs at x equals c in this graph. We can see that the limit exists, but the function value here is different. And in a, the function is just not defined there. So we call these removable discontinuities because they're just little holes that if we plugged them, the discontinuity would be removed. If we simply change the value of the function at that one point, all of a sudden the hole would be plugged and it would be continuous there. All right. So if we continue to look for places where our function is discontinuous, we can see that there's some sort of a discontinuity there, which we'll call b, just to keep everything in alphabetical order nicely along the x-axis. And this is a different type of discontinuity. We can't just plug the hole. It still ends up being discontinuous. The limit on the left and the limit on the right are different numbers, and we have a name for that as well. A jump discontinuity occurs when the limit as x approaches a from the left of f of x is not equal to the limit as x approaches a from the right of f of x. Basically, the left and right-handed limit exist, but they are different numbers, and so the function is continuous up until that point, and then it jumps either upward or could be downward to another value and then continues on from there. And in this problem, we have a jump discontinuity at x equals b. All right. There is one more type of discontinuity, and we can actually see it happening right here with this vertical asymptote. That is going to be d. We're going to call that d. And this is called an infinite discontinuity. And an infinite discontinuity occurs when any of the following are true. Either the limit as x approaches a of f of x is positive infinity or negative infinity, or just the left-handed limit is positive infinity or negative infinity, or the right-handed limit is positive infinity or negative infinity. Basically, we don't need for both sides to have limits of positive infinity or negative infinity, even if just one of them is asymptotic vertically, has a limit of positive infinity or negative infinity, that counts as an infinite discontinuity. Even if we had a situation, I'm going to just kind of draw this off to the side, where on one side we had a vertical asymptote, and then on the other side we didn't. The function was just disconnected there and fine. This still counts as an infinite discontinuity because in one direction, at least, that graph is going down towards infinity. And of course, in this problem, that occurs at x equals d. So those are the points where this graph is discontinuous, but everywhere else on this function's domain, it ends up being continuous. Basically, anywhere you're drawing a graph and you have to lift up your pencil to either make an open circle or to move to another part, counts as a discontinuity. Now, this is just a kind of generic function that I drew. We don't have an equation for this particular function. But in the video problems that I've done, we have a few examples where I give you the equation of a function and I ask you to use your knowledge of the functions and their graphs to figure out where the discontinuities are. I don't have any of those problems in the main instructional videos. Those are going to be example problems. So please make sure, even if you don't usually look at too many example problems, that you look at a couple of those for this lesson, because we don't get to any of these in the introductory videos. Those examples are very explicitly in the separate example videos. So please make sure you look at those, because we really want to be able to examine functions with their equations and not just with their graphs to figure out where some discontinuities happen.